Okay, welcome again. Uh, it's a pleasure to introduce today's speaker, Anne Wienhard, who received her PhD in 2004 from University of Bonn under the supervision of Werner Ballmann and Mark Berger. She is currently director of the Max Planck Institute for Mathematics in the Sciences in Leipzig, Germany, and her research is in the intersection of geometry, topology, and dynamical systems. Anne is world renowned for her work on Teichmüller theory. She is a member of several academies um, and a fellow of the American Mathematical Society. She was an invited speaker at the International Congress of Mathematicians in 2018 and at the European Congress of Mathematics in 2016 and delivered a plenary lecture at the European Congress of Mathematics in 2024. And please join me in welcoming Anna as she will give today's AMR-RMA distinguished lecture on a beautiful world beyond hyperbolic geometry, Anosov representations, and high Teichmüller spaces. Please, Anna.
Well, thank you very much, and thank you very much for the invitation to speak here. It's really a pleasure to be here, and yeah, I would like to give you in a nutshell what I want to do in basically the next hour in my talk. So I want to tell you something about recent developments in the study of discrete subgroups of Lie groups, and my motivation and somehow teaser into this problem really comes from looking at hyperbolic geometry. So if we have a hyperbolic manifold, its fundamental group naturally embeds as a discrete subgroup of the group of isometries of the hyperbolic plane, which is an indefinite orthogonal group. And these discrete subgroups of SO1n, of isometries of hyperbolic spaces, or more generally of other Lie groups as well, arise in many different settings. They arise as monodromies of differential equations. They arise as symmetry groups of tie lengths. So for example, of this tie length you see here on the slide, but they also arise from arithmetic constructions. And I'm not going to give you a complete picture or overview. I just want to give you a few or recall a few properties of discrete subgroups in hyperbolic space, somehow recall of you the beautiful word of hyperbolic geometry or some aspects of it, and then use this somehow and go and tell you a bit about recent development where we go from hyperbolic geometry to more non-positively curved geometries and look at arbitrary Lie groups like the special linear group, the symplectic group, and so on. So let's recall just hyperbolic geometry. I mean, you all know hyperbolic geometry, but let me just give some, just recall some of the properties of the model of the hyperbolic plane and hyperbolic three space, because I just want to also use this to then highlight certain similarities to the non-positively curved situation later. So our most classical or one of the best known models for hyperbolic space in dimension 2 is the Poincare disk model. So we think of the interior of a unit circle with a metric which is given by conformal rescaling of the Euclidean metric. This gives us a metric, Riemannian metric of constant curvature -1, and the group of isometries is, we can think of this as the group PSL2R, or in this model, it's sometimes better to think of it as PSU11. For hyperbolic free space, we have ball model in now two-dimensional ball, so interior, so three-dimensional ball, interior of a ball in R4, where the group of isometries, we can think of this as SO13 or as the group PSL2C, which acts by isometries on this space. And you also see that there's a very nice way of embedding the Poincare disk model into the Poincare ball model as the disk which is spanned by the equator. I want to highlight another model as well, the upper half plane model of a hyperbolic space in dimension 2. So here we can think of this as complex numbers with positive imaginary part, and the group SL2R acts on this by fractional linear transformation, so sending z to az plus b divided by cz plus d for matrix A, B, C, D of determinant 1. And I really want to think of SL2R, so the 2 by 2 matrix of determinant 1, better as a symplectic group, so as a group preserving a non-degenerate Q-symmetric bilinear form on R2. We will come back to this later. You will see why I prefer this kind of way of thinking about SL2R. And I want to highlight here also that this action by fractional linear transformation on this upper half plane actually extends also to the boundary, and the boundary you can identify with RP1 or R union infinity, and this action on the boundary actually preserves the orientation. So these are just the model geometry, so hyperbolic space in dimension 2 and hyperbolic space in dimension 3. So now we want to look at more interesting manifolds in particular, and start with hyperbolic surfaces. So we know by the uniformization theorem, any closed surface orientable of genus greater or equal than 2, so of negative Euler characteristic, can be endowed with a hyperbolic metric, and this we can actually realize it as a quotient of the hyperbolic plane by an action of a discrete subgroup of the group of isometry, so of our group PSL2R. There's not just one way to do that, there are many ways to do that, and so it's very nice to look at the space of all possible hyperbolic structures on a given topological surface. Look at this space of marked hyperbolic structures, which actually has a very nice parametrization. So it's homeomorphic to R to the 6g minus 6. And it plays an important role because it's a smooth cover of the Modely space of Riemann surfaces. Again, we use the uniformization theorem to take a Riemann surface structure and realize it by the unique hyperbolic metric in its conformal class. I also want to take one step back in some sense from geometry and look at Teichmüller, at this Teichmüller space or space of hyperbolic structures in a different way. So if I put a hyperbolic structure on my surface, I get an action of the fundamental group of this surface by deck transformation on the universal cover, which with the hyperbolic metric identifies with H2, with the hyperbolic plane. And I can remember, forget all the geometry and just remember this group homomorphism from the fundamental group of the surface into the isometry group of the hyperbolic plane, so into PSL2R. And if I do this, I actually retain all the information because I can recover my hyperbolic surface by looking at this action of the discrete group on the hyperbolic plane and going passing to the quotient. So I can think of this space of all marked hyperbolic structures on my surface as a subset of the variety of representations of homomorphism, fundamental group into PSL2R up to conjugation by PSL2R. And if I do that, these representation which arise as these holonomies of hyperbolic structures on the surface have a very nice property. They form a connected component where basically by being a holonomy of this hyperbolic structure, every group homomorphism is injective with discrete image. And so this is in some sense in the model or point of view of Teichmüller space, we want to keep in mind and come back later. So this is a situation in dimension 2. So we have, if I give you a hyperbolic surface, there are many ways of, if I give you a topological surface, there are many ways of putting a hyperbolic structure on it. And so there are many ways of embedding the fundamental group of this surface into the isometry group of the hyperbolic plane, such that I get a discrete subgroup of PSL2R. So now I want to step one step back and talk about something completely different, and then in the next slide make a connection. So now we forget all about surfaces. We just look at Diophantine equations, and we look at the Markov equation. It's the equation given by x squared plus y squared plus z squared minus 3xyz is equal to 0. And we are looking for integer solutions of this equation. Integer solutions, x, y, z, are called Markov triples. They are well studied in number theory. I'm not going to go into all the interesting questions and all the interesting things they are related to. But I want to, at this stage, observe one of the theorems of Markov when he introduces it, and every Markov triple actually can be obtained from the trivial solution you can write down when you just stare at this equation, namely the solution 1, 1, 1. By doing the following things, you can apply this move which sends x, y, z to a new triple where you just change x to x prime, which is y squared plus z squared over x, and you leave y and z untouched, and then you can permute your three variables, and then you do this kind of change of variables in one of the other variables. So when you do this, you get this Markov tree where you start with 1, 1, 1. So the next solution you create is 1, 1, 2, then 1, 2, 5, and so on and so on. So what do these Markov triples, these integer solutions to the Markov equation, have to do with hyperbolic surfaces? We actually get to Markov triples and the Markov equation when we try to understand hyperbolic structures on the one puncture torus. So we take a very simple surface, one puncture torus, and now we want to look at all finite volume hyperbolic structures on this one puncture torus and try to parameterize this space. I mean, we saw before this is a continuous space. We want to parameterize this. So here there are different ways of parametrizing this. Here's one way of parametrizing it, which goes back to Penner. So for this, we do the following. So we take this one puncture torus, we choose an ideal triangulation of this torus. So this is some topological input we need to parameterize this. So when we we pick this ideal triangulation. So this let me use the pointer. This is what you can see here. And now we basically want to take a parameterization by measuring the length of certain geodesic arcs. Of course, if we take an ideal triangulation, we measure the length of the side of a triangle. This is always infinite, but we can make it finite by the following trick. So we choose a small horse cycle around the puncture. And now if we look at our sides of the triangulation and intersect them with the horse cycle, we are left with a finite piece of this arc, and we can measure the length of this arc with respect to the hyperbolic metric we have on this one puncture torus. So this we can put in this setting. So we have our triangulation. So this is, we get these two triangles, and they are to form this one puncture torus. They are glued like that. So we have three parameters we can measure, the length of three geodesic arcs. So now we can change our topological to this ideal triangulation, because the hyperbolic structure doesn't depend on the ideal triangulation, and choose a different triangulation. And for example, choose one where we just take this quadrilateral, and instead of cutting it in this way, cut it in this way into two triangles. When we do this, by hyperbolic geometry, you can compute what is the new parameter for this geodesic arc, which you introduced here. And you see that this is given by the following equation. So coming from this, from the Ptolemy equation. So you get a new coordinate a prime, and a times a prime is equal to b squared plus c squared. So if we start with three parameters, a, b, c, our new parameters after flip are b squared plus c squared over a, b, c. This is precisely the move we saw for the Markov numbers. And so we start with 1, 1, 1, so an ideal triangulation and a hyperbolic structure where all these arcs have length 1. Then we get all the Markov numbers. So I also want to point out how you get actually not just the numbers, the solutions, but also the Markov equation out of that. In this construction, there's something which is independent of the triangulation we chose, namely we took this horse cycle, and the length of this horse cycle is only determined by the hyperbolic structure, not by the triangulation. So this is an invariant which stays the same even if we change our triangulation and change our parameters. So if you look at what is the length of the horse cycle in the parameters, it's given by 2 a squared plus b squared plus c squared over abc. And so if you compute this for 1, 1, 1, this is equal to 6. So this gives you back the Markov equation. So there's this nice interplay between, in some sense, Diophantine equation and hyperbolic surfaces. So now let's go one dimension higher and somehow look at the situation in hyperbolic geometry one dimension higher. It changes very drastically from the two-dimensional situation. So first, hyperbolic three manifolds are much, much more complicated than hyperbolic surfaces. They are, of course, very interesting because they arise in many different contexts. So in the geometrization conjecture, geometrization theorem of three manifolds. So to some extent, most three manifolds actually are hyperbolic. But they also rise as hyperbolic structures are not complements or mapping tori of pseudo-Anosov diffeomorphisms of surfaces. But now if we look at fundamental groups of closed hyperbolic three manifolds, by Mostow's rigidity result, there is no interesting moduli space like Teichmüller space there, because there's only up to conjugation a unique discrete faithful representation into the isometry group of hyperbolic three space. So in this situation, if we fix the fundamental group, if we fix the topology, it completely determines the geometry, the hyperbolic geometry on our manifold. So this is true for fundamental groups of closed hyperbolic manifold. So if you think of them as discrete subgroups of the isometry group of hyperbolic three space, these are lattices. So these are discrete subgroups of finite full volume, so where the quotient manifold is of finite volume. But of course, there are many interesting other discrete subgroups which are not lattices in the isometry group of hyperbolic three space. So they're named Kleinian groups after Felix Klein. And I want to illustrate to you three examples. Before I go to the example, I want to emphasize one important invariant which you can look at if you have a discrete subgroup of the isometry group of hyperbolic space. And you can look at what we call the limit set, so which is the following. So I take a point in hyperbolic space, I take the orbit under my discrete subgroup, and then I look at all the accumulation points of this orbit in the boundary. So best is to take the ball model, I compactify hyperbolic three space by the sphere at infinity, and then I can look at the accumulation points of an orbit of my group in the boundary. This is what we call the limit set, and this limit set often has very interesting information about your group and about your group action. So one class of Kleinian groups, which is in some sense characterized by the limit set, is the class of quasi-Fuchsian groups. So this is, we still have the group which is fundamental group of a surface, so abstract as the abstract group. If we let it act on the on hyperbolic three space, then this if we think of this then as a discrete subgroup of PSA to C, it's called a quasi-Fuchsian group if this limit set is a quasi-circle. So it's homeomorphic to a circle and cuts the sphere at infinity in two parts. So these are very interesting groups because they arise from taking a hyperbolic structure on the surface, or taking a Fuchsian group in SL2R, putting SL2R and SL2C, and then looking at small deformations. They are also very interesting because if you have one of these quasi-Fuchsian groups, you can look at, remove this quasi-circle, you have these two quasi-disks in the sphere, and if you look at the your quasi-Fuchsian group acting on these two disks, you get properly discontinuous actions. So the quotient, in the quotient, you get two surfaces which come with a complex projective structure because it's a subset of CP1 of the sphere at infinity, and in particular it also comes from a uniform from a conformal structure. So this is really what appears in the double uniformization theorem. So these are very interesting groups when your discrete subgroup is isomorphic to the fundamental group of your surface. There are generalizations of that which have less nice structure, but still a lot of nice structure, which are called convex co-compact subgroups. So if you start with a quasi-Fuchsian group, if you start with a Fuchsian group, it preserves this H2 embedded in H3. So it preserves a closed convex subset and acts on this subset co-compactly because the quotient is your your closed surface. If you deform slightly and you have a quasi-Fuchsian group, you can take the convex hull of this limit set of this quasi-circle, and your group would still act co-compactly on this now more complicated convex subset of H3. And more generally, you can define for an abstract group, which doesn't have to be fundamental group of a surface, but which, so abstract discrete subgroup of PSL2C, you call it convex co-compact if there's some closed convex subset of H3, which is preserved by your group gamma, and such that if you restrict the action of gamma to this convex subset, the action is properly discontinuous and has a compact quotient manifold. And so quasi-Fuchsian groups are examples, but there are many more examples, and we will come back to these convex co-compact subgroups in a bit. I want to mention one other group, which probably many of you know, which is not convex co-compact, but it's still a very interesting and nice discrete subgroup of PSL2C, namely the Apollonian group. So it's the symmetry group you get when you take an Apollonian circle packing. So you have three mutually tangent circles, and then you create the packing out of it. And if you look at the group, which is so subgroup of PSL2C, which is generated by inversions in the circle, this is the Apollonian group. It's an example of a geometrically finite Kleinian group, but not a convex co-compact one. And of course, it has, I mean, these Apollonian circle packings have a lot of interesting also arithmetic, a very interesting arithmetic story, which I'm not going to touch in this talk. So let me just summarize this classical results and picture for discrete subgroups of the isometry group of hyperbolic space in this somehow landscape of discrete subgroups. So we have lattices. They come in two flavors, co-compact lattices, so where the quotient of the hyperbolic space by the group is a compact manifold, and non-co-compact lattices where it's a non-compact finite volume hyperbolic manifold. Then we saw this class of convex co-compact subgroups. So these groups which preserve a convex subset, and this bigger class of geometrically finite subgroups. So why is this class of convex co-compact subgroups so interesting? Because it's a class of discrete subgroups which is dynamically stable. So if I give you a convex co-compact subgroup, and now you change the generators of this subgroup a little bit, but so that you still get a subgroup of the same topological type, it will be also convex co-compact. So this is a stable notion. The other thing which makes them interesting, and this is actually in the hyperbolic situation equivalent to being convex co-compact, is that these groups form quasi-isometric embeddings. So if you compare the length of the number of generators you need to write an element in your group, sorry, with respect to finite generating set, this is comparable with the distance between a base point and the image of this base point by your group element gamma in hyperbolic n space. They also, and we saw this a little bit for a quasi-Fuchsian representation, they give rise to interesting geometric structures on manifolds. There's also, and I will give one example of this a little bit later, a very interesting relation between growth of orbits of your discrete group or acting on hyperbolic space and the Hausdorff dimension of your limit set at infinity. And if you look at, again, quasi-Fuchsian groups, you can look at variations of the Hausdorff dimension of quasi-Fuchsian representation, and they actually give you rise to a metric on Teichmüller space, but I'm not going to go into detail there. So now what I want to do is leave the world of negative curvature, world of hyperbolic geometry, and go to the world of more general discrete subgroups of Lie groups, in particular Lie groups of higher rank. So Lie groups are called Lie groups of higher rank if the maximal subgroup, which is diagonalizable over the reals, is of dimension at least 2. And this has the feature that if you look at their symmetric space, so to each semi-simple or reductive Lie group, you can associate its symmetric space, which as a homogeneous space is just G modulo a maximal compact subgroup. If you are in higher rank, this space will be non-positively curved, but it will have planes, isometrically embedded Euclidean planes of 0 curvature. So you will not be negatively curved. So now we are interested in discrete subgroups of these higher ranked Lie groups. And again, of course, they come in 2 flavors. So one, they can be lattices. So then the quotient of your symmetric space by this discrete group is of finite volume, or they can be non-lattices, which is just everything else. So if the quotient is of infinite volume. So here are just these spaces, which I shortly described: H2 hyperbolic space in dimension 2, hyperbolic space in dimension 3. And in some sense, their natural higher rank generalization of this from SL to R mod SO2, you can go to SLN mod SO, SLN R mod SON, so the space of basically Euclidean scalar product on Rn. You can go from the symplectic group to Hn, the Siegel space, and also in the complex world. I want to give you one example now, a bit more of the geometry of one of these higher rank symmetric spaces, namely for this symplectic group. So this is the Siegel upper half space. And here's the model for it. You look at symmetric n by n matrices over the complex numbers, where the imaginary part is a positive definite matrix. And now you can act with the symplectic group, if you think of this as a 2 by 2 block matrix, in the same way by fractional linear transformation. This action again extends to the boundary, and in particular, it extends to some of the part where the imaginary part is 0, so where you just have a symmetric n by n matrix over the reals at infinity. It's a flat, if you look at what is these flat subspace, this Euclidean subspace which are embedded, you can think of this as having one, when you just take diagonal matrices with positive entries and then I times that. So this is has positive definite diagonal part. And the way I would like you to think about this is to really think of this as a hyperbolic plane over the space of matrices or symmetric matrices. So where in the upper half space model for the hyperbolic plane, we had R. We now replace R by symmetric n by n matrices and R plus by positive definite symmetric n by n matrix. So if you go, and we now, these discrete subgroups in higher rank Lie groups have been studied for a very long time. And one of the most striking results was Margulis superrigidity and Margulis arithmeticity theorems. Margulis works at lattices in higher rank Lie groups are super rigid. The situation is even more rigid than in Mostow rigidity. Basically, whenever you take a lattice in a higher rank Lie group, you take any unbounded homomorphism into any other Lie group, this extends to a Lie group homomorphism from your ambient Lie group G into G prime. So there's no flexibility for these lattices as well. And out of that, you can deduce Margulis arithmeticity. Every lattice in a higher rank Lie group actually comes from an arithmetic or number theoretic construction. So to some extent, we know everything about lattices. Of course, there are still many open questions which I'm not about lattices, which I'm not going to apply, but lattices in higher rank Lie groups are very rigid. So then you might ask, okay, so in the hyperbolic 3 space, we went from lattices to this convex co-compact subgroups, which were much richer and had a very nice structure. What happens if we do this for higher rank Lie groups? And Kleiner and Leib and Jean-François Marquin, independent from each other, showed that actually you don't gain anything from that. So if you look at a higher rank Lie group, and you take a discrete subgroup which preserves a closed convex set and acts co-compactly on this closed convex set, but is not secretly contained in another symmetric space, so in a smaller Lie group, then this group, this convex co-compact group, actually has to be a co-compact lattice. So convex co-compact is the same as co-compact lattice. So it, in some sense, raises this question, is there actually a nice class of discrete subgroups in higher rank, which is rich, but still has some structure theory? And so basically what I want to explain to you now, that I want to discuss a bit development of the past 20, 25 years about two interesting classes of discrete subgroups, named the class of Anosov representations. So these are discrete subgroups, which are, and I want to think of them more in terms of I want to change the point of view a little bit and not think of it as a discrete subgroup in my Lie group G, but take an arbitrary, somehow abstract, finitely generated group and think of ways of embedding this or mapping this group by a group homomorphism into my Lie group G. And so Anosov representations exist when you have a finitely generated group which in itself has negative curvature, so it's a hyperbolic group in the sense of Gromov, and G can be any reductive Lie group. And I want to show you some results, but what I want to tell you is that Anosov representations are really the right generalization of convex co-compact subgroups in this higher rank setting. So they give you a rich class of discrete subgroups. And then so we saw in hyperbolic 3 space that if we take convex co-compact subgroups and restrict this abstract finitely generated group to be the fundamental group of a surface, then we actually talk about quasi-Fuchsian representations. And so if we take in the general case of an arbitrary reductive group gamma to be a surface group, then actually there are classes of discrete subgroups or group representations which are very similar to Teichmüller space, seen as a connected component of the representation variety. And these go under the name of higher Teichmüller spaces. So these are discrete subgroups of certain families, special families of Lie groups, which have this nice property that there are connected components in the representation variety where every single representation is discrete and faithful. And basically now I want to tell you a little bit about these two classes of discrete subgroups. So in order to give you the definition of what an Anosov representation is, I need one key feature of these higher rank symmetric spaces, and that's what is called the vector value distance function. So if I'm in this higher rank symmetric space, and I want to look at what is the invariant of 2 points in this space up to the action of the group of isometries, it's not just a number, which is the distance between these 2 points, but actually the invariant is a vector. And I want to illustrate this in the case just of SLNR. What is this vector? What is this vector valued distance function? So if I have a matrix in SLNR and I look at this action on the symmetric space, so x0 is a point in my symmetric space, then this vector value distance function is the following. If I take the distance between x0 and its image by G, it's the log of the singular values of this n by n matrix of determinant 1. So this log of the singular values, their sum is 0. And so I can think of this as a vector in this Cartan subspace, so in the space of diagonal matrices lambda 1 up to lambda n, where the sum of the lambda I is 0, which is the Cartan subspace of SLNR. And so if I get as my vector value distance function a vector in this biochamber in A, and it can of course make out of this a real number by just choosing a linear form on A, for example. I can also choose a norm, but we want to choose linear forms, and we have special linear forms coming from the Lie theory, namely roots, which are just the linear forms which send lambda 1 to lambda n to lambda I minus lambda I plus 1, so to the difference between consecutive singular values. So what is now an Anosov representation? An Anosov representation is a group homomorphism of my finitely generated group gamma into SLNR, which looks like a quasi-isometry, but in a very strong way with respect to the vector value distance function and a simple root on the Cartan subspace. So a representation is called alpha I Anosov, where alpha I is this ith root. If there exist two constants, C1 and C2, such that if I take my element gamma of my representation, I take my base point and look at the vector value distance function between the base point and gamma times the base point, and I apply my simple root alpha I, then this has to grow at least as the word length of gamma in my finitely generated group, up to the scaling by these two constants, C1 and minus C2. So this tells you that if you take a longer and longer element in your group, and you take a simple root. So let's, for example, take the root alpha 1. So the kernel is this, would be this side. If you look at your elements, they go in this white chamber away from the wall in the linear fashion. So it's a very, very strong, it's not just quasi-isometry, it's a very strong form of quasi-isometry. So this notion of Anosov representation, has been introduced by François Laborie, and he also, I mean, this is not the original definition. This is a later characterization by Kapovic, Leib, and Porti, and independently Bocchi, Potri, and Sambarino. And there too, I want to highlight two properties of, or one property of Anosov representation, and then give you more, that this strong quasi-isometric property, so going away from the walls of the kernels of the roots, gives you that you have very strong boundary maps. So you will have maps from the boundary of your finitely generated group into the Grassmannian of I-planes in Rn, if you are alpha I Anosov. And you also have a map into the Grassmannian of n-minus I-planes. And these two maps have a very strong form of injectivity. Namely, if I take two distinct points in the boundary of my abstract finitely generated group, the two I-plane and n-minus I-plane will be in general position. So if you specify back to the groups we looked at, so I gave you the definition for SLNR, but you can give the definition for an arbitrary reductive Lie group. For PSL to C, Anosov representations are precisely convex co-compact representations, or more generally, for rank 1 Lie group, Anosov representations is the same as being a convex co-compact representation, so group homomorphism to a discrete convex co-compact subgroup. So I want to give you a couple of other examples of Anosov representations, and I mean, this shows you a bit what you can play around with. So the first thing you can play around with is you can take a convex co-compact subgroup of a rank 1 Lie group, take your rank 1 Lie group, put it into a Lie group of higher rank, and the composition will be Anosov in this higher rank Lie group with respect to some set of simple roots. So this you can compute explicitly. The main two examples are the following. So you take the fundamental group of a surface, embed it in SL2R as a co-compact lattice. Of course, this is a convex co-compact subgroup. And now take SL2R and embed it in SL3R. And there are two different ways we can embed. So we can embed as a block, or we can embed using the irreducible representation. And these two representations behave very differently, and we will see this in a later example. Another family which was studied much before Anosov representations were known under this name was what is called convex divisible representation. These were studied by Benoit. So you have a discrete subgroup of SLNR, and you ask for it to preserve a strictly convex domain in RP n-1, and such that the action on this domain is co-compact. This is a convex divisible representation. All these give you examples of Anosov representations. So I mentioned, and I will come back to this higher Teichmüller space later. So one example of this is when you do precisely that, you take fundamental group of a surface embedded as a co-compact lattice in SL2R, and now you cannot just go into SL3R, but you can actually go via the irreducible representation into SLNR. So take the irreducible representation of arbitrary dimension. If you do take this representation, and then any deformation of it will actually stay Anosov, will be an Anosov representation, and you get a connected component of the representation variety, and this connected component you get is known as the component of Hitchin representation. There's another class of representation which I'm not going to say much about, but which also gives you connected components where every representation is an Anosov representation. So it gives you one of these higher Teichmüller spaces. This is when you take fundamental groups of a surface into, for example, the symplectic group, or more generally a Hermitian Lie group. If you do this, there's a characteristic invariant, something like the Euler number for such a representation. If this Euler number is maximal, so assumes the maximal possible value, then you will be an Anosov representation. So these, the first examples I give you, they are all in some sense a nice convex co-compact subgroup in rank 1, put it in a higher rank Lie group. There are by now also interesting constructions and examples of groups which do not admit any discrete faithful representation in a rank 1 Lie group, but admit a nice Anosov representation in a higher rank Lie group. And things come from projectively convex co-compact subgroups, or cubulated groups, or amalgamation of groups. So there's a rich, these sets of Anosov representation give you rich class of discrete subgroups. They also have very nice properties. So any Anosov representation is discrete and faithful. So it really gives us a class of discrete subgroups. And this, the way I gave the definition, it's essentially clear. They, of course, I have a discrete subgroup of this reductive Lie group. I act properly discontinuously by isometries on the symmetric space. But now, because my group is a hyperbolic group and my space has non-positive curvature, but not negative curvature, the quotient will essentially always be a locally symmetric space of infinite volume. So I'm always, if my group is really true higher rank Lie group, I'm not a lattice at all. The orbit map is again a quasi-isometric embedding, and this is, I sold you this definition for an Anosov representation as a much stronger property than quasi-isometric embedding. The other, and this was the, in some sense, motivation for François Labourie when he introduced this, is dynamic stability. So the set of Anosov representations in the representation variety is an open set. If you like dynamics, it's also a very nice way of thinking about Anosov representation as reparameterizations of the geodesic flow. And this is actually a very useful picture for some of the applications. But there are now, I mean, this, I would say, are key properties. There are now many other properties of Anosov representation. I would just want to highlight basically three aspects of Anosov representation. So the first aspect I want to highlight is the connection with now geometric structures on manifolds, again, or the connection with domains of discontinuity. So we saw for quasi-function representations, if we remove this quasi-circle, our group acts properly discontinuously on the complement of this limit set in CP1, and we actually get two surfaces with a complex projective structure. So a similar but more complicated construction you can essentially do for any Anosov representation. So if you have an Anosov representation, you can find domains of discontinuity in flag varieties for your group G. So for example, space of full flags or the space of Grassmannians, depends on your, with respect to which roots you are Anosov. And if you look at the quotient, you get a closed manifold. In many cases, this closed manifold will actually be related to your finitely generated group. So if you took your finitely generated group to be the fundamental group of, say, hyperbolic manifold, for example, in many cases, this domain of discontinuity and its quotient, when you construct it, is actually a fiber bundle over this compact manifold. So this is a very versatile construction, which you can also use, for example, in situations to look at this infinite volume locally symmetric spaces and construct explicit compactifications of this infinite volume locally symmetric spaces. So this is domains of discontinuity. So we have a nice generalization of this. Another aspect I want to highlight shortly is this connection between Hausdorff dimension and orbit growth, or this question, actually, if we have an Anosov representation, how does the limit set of such an Anosov representation look like? And actually, this is very interesting because now in higher rank, you see phenomena you don't see in the rank 1 situation. So in hyperbolic geometry, Bowen in the 70s showed that the limit set essentially is either smooth or it's a fractal curve. So in particular, he showed if you have a quasi-Fuchsian representation, the Hausdorff dimension of the limit set is bigger or equal than 1, with equality if and only if you preserve H2 sitting in H3, so if you have Fuchsian. So now in the higher rank situation, you get new phenomena. You have an Anosov representation where you have limit sets which are rectifiable, but not smooth. You have limit sets which are C1 smooth, but nowhere C2. You have, of course, also smooth limit sets, and you also have things which are fractal. And I mean, here, just wanted to give you this one example. When you take these two different embeddings of SL2R, the limit set you get has quite different flavor. And you can, in a similar way than classical results of Sullivan for hyperbolic geometry, you can actually make a relation between orbit growth or better certain entropy functions of your discrete subgroup and the Hausdorff dimension of the limit set. And this, I just want to highlight, this is a point where we understand some things, but where there are still a lot of open questions to understand this precise connection between the two. So the third aspect I want to just highlight, which again is something where we understand something, but where there are a lot of open questions, is how does the space of Anosov representations look like? So it's an open subset of the representation variety. It's if we're not in these special situations of higher Teichmüller spaces, it's usually not closed. It can be very complicated. And basically, the only case in higher rank, there are only two cases where we understand fully the space of Anosov representation. One is for certain triangle groups, and there the representation variety is one-dimensional, so it's not so hard. It's still hard, but not so hard to understand the space of Anosov representation. And the other is the modular group in SL3R, and this is very recent work from this year by Rich Schwartz, which relates to Pappos theorem and representation constructed out of Pappos theorem. So here too, you see two pictures where Emile Dumas and Florian Stecker try to numerically understand how does the space of Anosov representation or a specific connected component looks like. So one is if you take this irreducible representation into SL3R, which is like these Hitchin representations, which are like a higher Teichmüller space, but now you embed it in SL3C. So it's really like the higher rank situation of quasi-Fuchsian representation. So it looks quite interesting, this space. And this is, as I said, it's just, numerically no proof at all what the structure of the space is. And the other picture comes from when you take this other embedding, when you embed SL2R as a block, and then again you embed into SL3C, and you want to understand how do these deformations of these real embeddings look like, just the ones which stay Anosov representations. So let me just in this slide highlight some of the I think problems and situations people are currently interested in or recently proved some results. So there's this question of which hyperbolic groups admit Anosov representations. There are questions about extending Anosov representation, so towards geometrically finite subgroups of higher rank, or also to understand better which are classes of subgroups which are quasi-isometric embeddings and dynamically stable, but are not necessarily Anosov. There are questions about counting problems and homogeneous dynamics on these now infinite volume locally symmetric spaces coming from Anosov representations. There are questions of arithmetic properties of Anosov representations, spectral properties of the quotient manifolds, finer structure for fundamental domains, explicit deformation. So how do you move in the space of Anosov representation, and also first results towards generalizing Bayer's double uniformization theorem in higher rank. So let me just summarize this by giving you a picture of the landscape of discrete subgroups in higher rank, which, I mean, it's due to, this picture is due to Theo Weissman, and it's of course much more difficult and rich picture than in the rank 1 situation. And so here we have this Anosov set of Anosov representations, which in the rank 1 is just convex co-compact, but in the higher rank it's very nice, but much bigger class of groups. So now I want to, in the last 10 minutes, to tell you a bit about higher Teichmüller spaces, which are these even nicer families in some sense. They are all Anosov representations, but they have this, okay, so one restriction. So now we focus on finitely generated groups, which are fundamental groups of surfaces. And now we don't just want open subsets of discrete and faithful representations, but we want higher Teichmüller spaces by which we understand really connected components of the representation variety, where every representation is discrete and faithful. So we want a situation where we don't just have openness of this nice set of discrete and faithful representation, but open and closeness. So since we take our fundamental group, our finitely generated group to be the fundamental group of a surface, which is a two-dimensional manifold, which admits a nice conformal structure, well, there's actually a nice connection between studying the representation variety through studying local systems, which you can do for any manifold, but then to studying so Higgs bundles, so holomorphic objects on Riemann surfaces. This gives you many different tools to study this representation variety. I'm not going to really go into this and tell you something about it, but it's very useful to switch point of view depending on the problem you study. So in order to go and give you a bit of a feeling of what these higher Teichmüller spaces are and when they exist, I want to just go back to Teichmüller space and recall a fact from hyperbolic geometry that we can actually characterize the holonomies of hyperbolic structures in the following sense, so in terms of some positivity. So if we have a representation from the fundamental group of the surface into PSL2R, then we can look at the boundary of this fundamental group of the surface, which topologically is a circle with a cyclic orientation, and the boundary of H2, which we can identify with RP1 as the boundary of the disk or the upper half space, which also comes with a natural orientation. And a representation, so group homomorphism, is a holonomy of hyperbolic structure if and only if you find a row equivariant map between the boundary of the surface, so between this 1S1 and the boundary of the hyperbolic plane, which sends positive triplets to positive triplets. And so this is now actually one thing which I want to tell you, that there's a very, very similar characterization and actually structure which is responsible for the existence of higher Teichmüller spaces. So as I mentioned before, what I consider as a higher Teichmüller space is a union of connected components of representation of the fundamental group of the surface into a Lie group G that consists entirely of discrete and faithful representations. And we already saw as examples of Anosov representations, in some sense, examples of these two families. So one family which was introduced by Hitchin and is now called the Hitchin component, is when G is a split Lie group. So here I just list the classical ones, SLN, sp2n, or orthogonal groups with signature n plus 1, or nn. Then Hitchin showed that there's a connected component, which is homomorphic to a ball of dimension 2g, to a vector space of dimension 2g minus 2 times the dimension of your group. And Labourie and Fock and Goncharov showed independently that points in this Hitchin component are discrete and faithful. And Fock and Goncharov actually links this to Lustig total positivity. For maximal representations, I told you there's this kind of generalization of the Euler number for Lie groups of Hermitian type. And if you look at maximal representations, we showed with Mark Burger and Alessandro Iozzi many years ago that these are all discrete and faithful representations. So these also gives you connected components of the representation variety, which are just discrete and faithful representation, but now they have non-trivial topology, and you can actually characterize them in some sense in terms of causal structures or positive Lie semigroups. So now what I want to explain to you a little bit is that there's some notion of positivity which includes the Lustig total positivity and positive semigroups, which actually gives you in some sense the common underlying structure for higher Teichmüller spaces. And for this, let me I'm not going to give you full definition. I want to highlight this on the flag variety. So we saw for a hyperbolic space, we characterized it as a map from S1 into RP1, which I think of the flag variety for SL2, which maps positive triples in SL1 to positive triples in this RP1. And you can characterize Hitchin representation and maximal representation in a similar way. And I want to illustrate this for the symplectic group. So there are two ways to define a notion of positive triples in flag varieties. And which flag variety you go into depends on a subset of simple roots. So if you work with the Hitchin component, you want to take all simple roots and you want to go in the full flag variety. And so if you have full flag for sp2 and R, these are isotropic families of isotropic subspaces. And you can always, if you have a triple which is pairwise transverse, you can write the fix your two outer to be their standard flags, and then you can write the third one as image of a upper triangular matrix times f minus, and you call this triple positive if this upper triangular matrix is a totally positive matrix. So a matrix where every minor which is allowed to be non-zero is actually positive. You get another way of positivity of triples in the space of Lagrangians, which comes from the Maslov index, but I want to illustrate it in a similar way as in the full flag variety. So you take three Lagrangians, you take L plus and L minus to be your standard Lagrangians. You write the third one, if it's transverse, you can write it as a image under this upper block triangular matrix, and you call this triple positive if this matrix M is a positive definite symmetric matrix. And so then you can actually characterize these Hitchin components and maximal representations in this terms. And I don't want to give it to you now for these two families, but I want to give it in this more general setting of positivity. So you can generalize this notion of positive triples and flag varieties and look at an arbitrary semi-simple or simple Lie group and ask basically when do we have a good notion of positivity of triples. And when you do that, you get four families of Lie groups. So you get split Lie groups, you get Lie groups of Hermitian type, which are of tube type. So these relate to the two positive structures I just told you for the Hitchin component and for maximal representation. Then you get two new families, so indefinite orthogonal groups and an exceptional family. And if you have this notion of positivity of triples in a flag variety, you can define or call a representation positive if and only if you have such row equivalent map from the boundary of your surface group, so this S1 into this flag variety, which sends positive triples to positive triples. And now, if you do this, you can actually prove, and it took us quite a few years to actually do this, that if you take this set of positive representations, so defined in this way, this actually is a higher Teichmüller space. So it gives you a set which is open and which is closed, and actually prove that any positive representation is an Anosov representation, so it's also discrete and faithful. And to prove closeness, this is the hardest part. I would say you actually do something like a generalization of the classical hyperbolic geometry color lemma, that if you have two intersecting curves, if one is short, the other is long, and you can prove an appropriate higher rank situation of this. But what I would like to illustrate that, I mean, this is in some sense motivated by this study of higher Teichmüller theory, but this notion of positivity actually gives you more. So it allows you to think of the symplectic group, for example, or more generally the Mission-Lie group of tube type as a group of type SL2, like an SL2 theory, but over a non-commutative ring with involution. And this we gave more details to that in work also with Bernstein, Retak, Alessandrini, and Rogozinnikov. You can actually now use this to get new models of the symmetric space for some complex Lie groups. You get non-commutative generalization of Thurston shear coordinates, non-commutative, I mean, realizations of Bernstein and Retak's non-commutative cluster algebra, and non-commutative Markov numbers. I want to now show you two slides to illustrate this non-commutative Markov numbers. But before I do that, I want to say that it also suggests many more things so basically take your favorite SL2R problem, and now it suggests certain non-commutative generalization of that. And I want to just illustrate this with non-commutative Markov numbers. And so for this, we now look at abstractly, so we forget about hyperbolic structures, but we keep this triangulation. And I mean, we in some sense keep the cluster algebra structure, which is behind that. And now when you use the Bernstein-Retak non-commutative cluster algebra, or use non-commutative coordinates for symplectic representations, you can somehow take this triangulation. So now we assign to sides of this triangle not a real number, but we assign to it a matrix, an n by n matrix. We have certain triangle conditions. So when you take A, B, C, here you want to make sure that this expression of these three matrices, where T is the matrix transpose, is actually a symmetric matrix. And then you can define the flip. So you go from, if you flip this edge, or you do a mutation in the corresponding cluster algebra, you go from ABC to A prime C B transpose, where A prime has this special form. And if you take a 1-by-1 matrix, so everything commutes, it's the same formula as you saw for the Markov number. You also have some Markov function, so an invariant function, which does not depend on your triangulation, so which is the sum of these parts, which, I mean, you can think of some non-commutative angles, which do not depend on the triangulation. And so now you can basically build what you did with Markov numbers, but just with matrices. You have to be a bit careful to satisfy this thing, but there's an easy way to do this. So for example, if you start with three matrices, the identity matrix, the upper triangular matrix 1T01 and 1 minus T01. This satisfies this property. Now, if you do this sequence of flips or mutations, you get matrices. If you take half of their trace, you get polynomials in T. If you specify them at T equals 0, you just get back Markov numbers. So you can think of this as some kind of non-commutative generalization of Markov numbers, but you can actually play around with this much more generally. So you don't need n by n matrices. You can do the same thing by just taking any ring with an anti-involution. And so you can even apply this to a commutative ring like the complex numbers, but with a non-trivial anti-involution. So when you take complex conjugation as anti-involution, then you can start with a Markov triple, which is not 1, 1, 1, but which is 3 roots of unity. And you get, when you do this and you mutate, you get a sequence of complex Markov numbers where the norm is just a real Markov number, but the argument now also mutates and gives you a family of arguments. And they're very interesting questions. So for example, what are the properties of the arguments? If you, for example, start with this root of unity, what arguments arise if you mutate forever? And so with this, I would like to stop and just show you in some pictures again. And I hope that I could tell you a little bit about that there's a beautiful world beyond hyperbolic geometry, and there's still a lot of things to discover, and actually to discover from many different directions of mathematics. Thank you.
Thank you so much for this beautiful and really inspiring talk. Are there any questions, comments?
Let me ask a very naive question. So in this last slide that you showed, so with this non-commutative Markov numbers, so I suspect there is some kind of quantum interpretation of this, right?
Well, not okay. So there's no, I don't know of a so I don't know of really a quantum interpretation of that. There is a there's a quantization of this picture, and
okay.
This is actually so there is. I mean, it's you can even before doing this Markov numbers, if you build this SL2 over, so you can basically build this SL2, but I like to. I mean, it's better an SP2 over this non-commutative ring with involution. And then you can write down very natural quantization, so this is like an SL2 over, so you can write down a very natural quantum group of that. This actually bears a lot of similarity with work of Manin. So there's these Manin matrices, which you used to write down a quantum SL2, but I think it's more natural because it's really the only relations you ever need are these relations of being in the symplectic group. And you need no other commutativity relation or anything in your ring. And there's one big difference when you do this, when you build the quantum group, is that actually there are not just, you don't have to necessarily look at the ring of functions, but you can actually look at the group and there are points in the quantum group. Because, and sometimes you start with something which is non-commutative and now you make it a bit more non-commutative, but the change is less drastic than going from classical SL2 to the SL2 quantum group.
Thanks.
More questions? More comments?
Well, let me ask another question. So when you were showing the slide with like other directions and open questions, so you mentioned something about spectral aspects of Anosov representations. Can you say a few words about that?
Yes. So basically, it's the question. So now, I mean, you look at. So it's really a question of the spectral aspect of this infinite volume locally symmetric spaces.
So you're talking about resonances, rather?
Yes, for example, resonance. I mean, there are different questions. So there, for example, a question when you take L2, is it tempered or not? There are all kind of questions. People started to look at resonances, and sometimes the way I see this is, I mean, the Anosov representation gives you the tamest infinite volume locally symmetric spaces you can have, in a sense. So it's really, because they have, I mean, they're also tame really in the topologic, so you can compactify them. You can actually, I mean, understand, I mean, you have to make a choice in which way you, I mean, with respect to which compactification of the symmetric space you want to compactify them, but you can very nicely describe the strata you add at infinity, so they're very tame, and so people start so they're really in some sense, best infinite volume locally symmetric spaces to try to understand properties of spectrum of Laplacian resonances and all that things.
I see. Thanks.
More questions? If not, then let's just thank Anna again.
Thanks.
Thank you very much.
Thank you.
Thank you.
Thank you.